Thank you, Gary. So, let's see, is it working? I guess it is. Okay, so G will always be a group, and X will be an abelian group on which G acts. And if there are any topologies involved, I'm going to ignore them pretty much, but everything will be continuous when it needs to be. Okay, well, when you're giving an expository talk like this, the first thing to do is start out elementarily enough that the experts fall asleep. So we'll start with defining H0. And this will just be, well, what I'll denote X upper G is just the set of X in X such that Gx equals X for all G. So it's just things fixed by the action, fixed points of the action of G. Okay, well, the nice thing about H naught is it's, if you know anything really about how G acts on X, this is something you can actually compute, as opposed to the higher cohomology groups, which sometimes get a little harder to compute. So I'll give one example. So let's let K be a field, and K bar is a separable closure, or you can take algebraic closure if you want. And I'll let GK be the, because all the fields we'll be working with are perfect, so algebraic is good enough. We take Galois group K bar over K, and we'll take X. We'll just take the multiplicative group of K bar. Then you have H0 of GK with coefficients in K bar cross. Well, that's just the things in K bar fixed by the Galois group. Well, that's just Galois theory. That's K cross. Okay, well, that's all I'm going to say about H naught for the minute, because there really isn't much to say about it. Now I'll skip H1 and I'll go to H2. I'll come back to H1. H1 is where all the excitement is. So I just want to get H2 out of the way. You really don't have to know much about H2, except we have to mention it exists. And beyond H2, we don't need it. So H2 of G with coefficients in X, well, we can describe as cocycles modulo coboundaries. And what are cocycles? Cocycles are just functions from G cross G to X. So these are just maps of sets. If you have topologies, you make them continuous. And they satisfy, and this is something you don't memorize, G1. There's a better form of this, which I put in the notes, where you change F to being a homogeneous function on G cross G cross G, but for our purposes, we don't need that. And then that makes this relation look a little more natural. In fact, everything I say is contained in the notes, and there's even more in the notes. So if you're taking notes, you can stop and let your hands rest. And now, what's this G1 doing outside here? Well, F is mapping into X in G1, X on X. So this makes sense. And let's see, we need one more term. So anyway, F satisfies this horrible-looking relation. It comes up naturally, but anyway, we'll never need this for anything. It's just what a cocycle is. And F is a coboundary means there exists a function h mapping G to X such that F of G1, G2 is G1 h of G2 minus h of the product G1, G2 plus h of G1. Well, it's easy to check that if F satisfies this, it actually satisfies this relation. So the co-boundaries are contained in the cocycles. They form groups, and you just mod out, and that gives you H2. Well, that shouldn't be very enlightening. So let me, I want to give one or two examples. Okay, so how are we going to get an element of H2? We need to write down a cocycle. So what are we going to do? We're going to look at, P is going to be a prime, of course, and we're going to look at QP, and we're going to get, GP will be the Galois group, and this is a notation I'll use throughout my talks, the absolute Galois group of QP. Okay, and we'll take A and B in QP cross. And let's take A not equal to a square. So then we can define F of G1 and G2, where G1 and G2 are coming from the only group we have here, GP, to be B, or 1. B is if G1 of square root of A is minus square root of A, and G2 of square root of A is minus square root of A, and 1 otherwise. Well, it's a straightforward check to see that F is a cocycle. So, therefore, F gives, well, I'll call it F again, in H2, GP, coefficients I'll actually take in something bigger than QP, namely QP bar cross. Now, of course, the question is, when is this cohomology class we get, when is it trivial? So when is F actually a coboundary? So, let's suppose B is a norm from QP of square root of A down to QP of something x plus y square root of A. So x and y are in QP. So suppose B is a norm from square root of A. So this just says B is, can be written in the form x squared minus ay squared. Okay, well, we can define, if B is of this form, we can define we can define an H. So define H of G to be x plus y squared of A if G root A is minus root A, and 1, well, if the only other choice happens, is plus root A. Oh. Try again. Okay, so it's a straightforward calculation to see that in this case, G, H, the coboundary of H gives you F. Namely, well, here the groups are all written multiplicatively, so instead of having addition, which is what we have over there, we have the usual problem with multiplication, and it's easy to see that if you write F of G1 and G2, that's G1 h of G2 times h of G1 divided by h of G1, G2, which you can see is exactly this relation here. So we get that B is a norm implies F is trivial. It's a trivial cohomology class. And conversely, and this is harder to show, actually, because see this, I didn't really use anything about the p-adics to get this way. But the converse, you have to use something that you're working with some field like the p-adics. This is true. Well, you might have, if you read, for instance, Sayre's course in arithmetic, you might remember the Hilbert symbol. Okay, so this symbol, AB sub p, is minus 1. Well, let's make it plus 1. If B is a norm from QP squared of A, and minus 1 if not. Well, you can see that means that F is essentially giving us the Hilbert symbol. Because F is trivial exactly when the Hilbert symbol comes out plus 1, and F is non-trivial exactly when the Hilbert symbol comes out minus 1. So the Hilbert symbol you can regard as corresponding to some element of some H2. We can say a little bit more along this line. Namely, there's several equivalent formulations of how the Hilbert symbol works. We can also write AB sub p equals, well, plus 1 or minus 1. And this is if and only if. If we look at sort of a generalized quaternion algebra, where you take QP and add on, let's say, symbols I, J, and K, where you have I squared equals A, J squared equals B, and K squared equals minus AB, and the usual other stuff, just like the usual quaternions. If this is a, let's see, in this case, it'd be, well, just be 2 by 2 matrices, M2 of QP, and in this case, it'd be a division algebra. Corresponding to these two cases. So either you end up with 2 by 2 matrices, which is, of course, an algebra, just doesn't happen to be a division algebra, or you end up with a division algebra, corresponding to two cases of Hilbert symbol. So more generally, if you look at H2 with, and take the group as being GK, the Galois group of field K, take coefficients in K bar cross, this classifies central simple algebras over K, of which these are two examples. Let's see. Oh. Ah. Okay, so the one result we need on H2 is the following proposition. If we take H2 of, let's say, the p-adics, coefficients in QP bar cross, this is isomorphic to Q mod Z. Okay, I won't prove this. This is one of the major results in local class field theory. But for example, this Hilbert symbol, sort of our F, which corresponds to the AB sub p, it corresponds to 0 or 1/2. 0 if AB sub p is +1 and -1, it gives us the 1/2. So what we were looking at was really just sort of the quadratic situation that's sitting inside this much bigger Q mod Z. Okay, so that's enough for H2 for the minute. So the real thing we want to look at is H1. So H1 of group G, coefficients in X, again, is cocycles mod coboundaries. And a cocycle is just an F mapping G to X, just any old map of sets, continuous if you have topologies around, such that, well, it's almost a homomorphism. F of G1 times G2 is F of G1, so I'm writing X additively, plus G1 F of G2. So this is sometimes called a crossed homomorphism. Because if you didn't have the G1 here, of course, it would just say you have a homomorphism. In fact, that's what will happen if the action of G1 on X is trivial, because then this G1 you can just ignore. Okay, what's a coboundary? Well, so F equals a coboundary means there exists an X in X such that F of G equals Gx minus X for all G. And sure enough, if you take something that looks like this, it will satisfy this relation. In fact, later when we try to construct cocycles, we'll see that we'll use essentially writing down things like this where X will come from some bigger set. And then we'll automatically, something looking like this will automatically satisfy a relation like this. And just if the X comes from the set we're looking at, then we actually have a coboundary. Okay, well, as I was saying, if the action is trivial, the crossed homomorphism just becomes a homomorphism. So that's the first case we'll look at. So let's suppose Gx equals X for all G and X. So that's just trivial action. Well, let's look what happens up here. Then the little G1 on the right doesn't do anything, so we can ignore it. So we get F of G1, G2 is F of G1 plus F of G2. So F's a homomorphism. So a cocycle is just a homomorphism. What's a coboundary? Well, if Gx equals X, then Gx minus X is 0. So the coboundaries are just 0. So you're not modding out by anything. So all you have is homomorphisms mod nothing. So we get actually H1 of G, coefficients in X, is just homomorphisms. These are just homomorphisms as, well, I guess this isn't really a Z module. It's just group homomorphisms from G to X. And of course, if you're working with topologies, they become continuous homomorphisms. So just an example, let's say K doesn't have characteristic 2, I guess. Well, let's not worry about that. Let's take x is z mod 2z. Okay, and whenever you write something like this, it's going to have trivial action. Well, I guess this has to have trivial action anyway. So h1 of g with these coefficients is just, now I'm going to take g to be gk for k of field. This will just be homomorphisms from gk to z mod 2z. And this just corresponds to quadratic or trivial extensions of k. How does a correspondence go? Well, if you have a homomorphism, it has a kernel. The fixed field of the kernel is a quadratic extension. Unless you take the trivial homomorphism and then, so I should really put trivial or quadratic extensions. Because if you take the trivial homomorphism, the kernel's everything, its fixed field is, of course, just k. Okay, let's take a different situation now. So you see, if the action's trivial, everything's fairly easy. Let's take another case where we can actually calculate h1. A lot of times h1 becomes hard to calculate, but there's a few cases where we can do it. So let's now suppose g is finite cyclic. Okay, so it's just g, with g to the n is 1. And x is anything. I'm not doing trivial action anymore. Well, let's let f be a cocycle. Well, we can do calculations like f of g squared, just using the cocycle relation, is f of g plus g times f of g. So I'll write that as 1 plus g times f of g. And if you keep going by induction, you get f of g to the I is 1 plus g plus g to the I minus 1 times f of g. So this just means take all the actions, add them up, and you get another element of x. And then you get f of g to the n. Well, that's the same thing as f of 1. And it's very easy to deduce from the cocycle relation, the cross homomorphism property, that f of 1 has to be 0. So that's 1 plus g to the n minus 1 times f of g. Well, this is just the sum of all the elements in the group. Well, I guess I probably should call it trace, but I'm going to call it norm. I mean, there's always this problem, as anybody who's taught abstract algebra knows, between additive and multiplicative notation. So that's the norm of f of g. So we see that we have to have the norm, or trace, whatever, of f of g come out 0 or 1 or whatever you want to call it. So that's life. Let's see. Okay, so also you can see from this calculation that once you know what f of g is, you know what f of every power of g, so you know the whole values of the cocycle. So just like a homomorphism from a cyclic group, crossed homomorphism coming out of a cyclic group is determined by the generator. So what we find out by just looking at this calculation is f of g, where g is cyclic, acting on x, is just the kernel of the norm. And what do we mod out by? Well, if you just trace through what the co-boundaries are, it's just things g minus 1 times x. So h1 has a very simple description in the case of a cyclic group. Now, we can also look at this for infinite cyclic groups. So the one infinite cyclic group we're interested in is, let's take the Galois group of an algebraic closure of a finite field, Fp, like this. So this is infinite cyclic, profinite cyclic, I guess is the way we should say it. It's generated by the Frobenius sub p. And you can say it's a profinite completion of an infinite cyclic group. Essentially, you do the same calculations. You've got to worry a little bit about continuity. But you see, you never come back to g to the n equals 1. So you never have this condition about the norm. And you actually get h1 of g in this case. And we better make x finite. You need that to make sure everything works. It's just x mod g minus 1 times x. So it's essentially the same thing, just you don't need the whole kernel, you don't need the kernel of norm, you get actually all of x. What's that? G is equal, where all the equals are transitive. Yeah, little g. Little g is Frob, yes, thanks. That's Frob sub p. Okay, so in this case of a finite cyclic group, we've actually seen things like this. Remember Hilbert Theorem 90. I don't call it Hilbert's Theorem 90 because it's actually due to Kummer. Well, essentially, there's one little point in the proof of Theorem 90 you have to worry about something being non-zero. And Kummer says just adjust it a little bit. And I guess Hilbert actually proved how to adjust it, or that you could adjust it. Anyway, it says if you have a Galois group, let's say L over K cyclic, let's say finite cyclic, generated by some G, and if, let's say X in L cross, and let's say the norm of X is 1, implies X equals Y, well, you can write it in the form gy over y for some y in L. Okay, well, you've all seen this theorem, presumably. What does this say? This just says, this is equivalent to just saying that H1 of our Galois group, L over K, coefficients in L cross, is 0. Because it says anything in the kernel of the norm is of the form, see, we could write this as y to the g minus 1. I mean, g minus 1 acting on y, which is exactly what we're modding out. So really, Hilbert Theorem 90 is just a cohomology calculation. In fact, more generally, so we can just erase and say, more generally, this equals 0 for all Galois extensions. L over K, even infinite if you want. So this is actually something useful. So to use it, we need the long exact sequence from cohomology. Well, any cohomology theory that's reasonable has something like this happen. So here, let's say G is just their group. A, B, and C are, well, called G modules. So just Abelian groups on which G is acting. And let's say we have 0 to A to B to C to 0 is exact. And it's an exact sequence of G modules. Okay, then, well, I'm going to write hi of G with coefficients in A is hi of A etc. We have 0 goes to H0 of A, H0B, H0C, H1A. Just keeps going, the numbers keep going up, it goes on forever. Well, I didn't define H3 and higher, but it keeps going up through those also. So, so how can we use this Theorem 90? Well, let's take K as a field, and we take the exact sequence 1 goes to mu n, where this is just the nth roots of 1. I'm assuming the characteristic of the field we're looking at doesn't divide n. Goes to k bar cross, goes to k bar cross, goes to 1. And this is just the nth power map. Okay, let's write down the cohomology sequence. Let's say G is going to be GK. So the cohomology sequence has H0 of GK. I mean, all these things have the Galois group of k bar over k acting on them. So we get k bar cross to H0 GK k bar cross. And this will just be the nth power map. You just look at how H0s are defined. It has to be that. This goes to H1 of GK coefficients in mu n. Goes to H1 GK k bar cross. And this is 0. This is k cross. This is k cross. This is something we don't know what it is yet, but this is the nth power map. And so what we get is k cross mod k cross to the nth power is it working? Good. Okay. Is isomorphic to H1 GK mu n. That's because with this being 0, it says this map is surjective, and we just sort through what the exact sequence says. And so this is a consequence of Hilbert Theorem 90. So for instance, you could take n equals 2, then you get mu 2, which in some sense is the same as z2, in other senses it's not. And this is gk x on mu 2 trivially. So you get homomorphisms from g into plus or minus 1. That corresponds again to quadratic extensions. This will just give the field mod squares. This just gives the thing you take the square root of to get the quadratic extension. That's all it is. Okay, well, in the long exact sequence there, we changed the module. We named A to B to C. There's also something that happens if you change the group. So let's say we have H is a normal subgroup of G. And we again have our X that everything acts on. Then we can actually have what's called the inflation restriction sequence. So it starts out with an H1 actually of G mod H. Now G mod H can't act on all of X. I mean, it's not a well-defined action usually. So you have to take the part of X that's fixed by H. Now that maps to H1 of G coefficients in X. How do we get that? Well, think of this as a function from G mod H to X. It just happens to end up with the cocycle is just a function from G mod H to X. happens to end up in xh? Well, a function from g mod h to x you can regard as a function from g to x that just happens to be constant on cosets. So you get a function from g to x. The fact it satisfies a cocycle relation here makes it work perfectly well over here. And now you can keep going. The real thing here is that that's an injection. So this goes to h1, h, coefficients in x. And this is actually all I need, but there's actually an action of g mod h on this. And so we actually can take the things in this cohomology class, in this cohomology group that are fixed by g mod h. But if you don't like this, you can just ignore it. Because I'm not going to go any farther. You can actually go on to a couple terms with h2s. I put that in the notes, but along with the action of g mod h on h1. But we don't need that. So how do you get from here to here? This is a function from g to x. Just restrict it. So this is restriction. And so therefore that's inflation. This is just taking a function from g to x and, and regarding it as a function from h to x. It's a smaller domain, that's all. Okay, how do we use something like this? Well, the main application we want is G will be GP. Okay, just recall this is Galois group of QP bar over QP. If we're looking globally, we'd call this a decomposition group, but all we're looking right now is at QP. So, and we'll take H, be what I'll call I sub P. This is the inertia subgroup. So just, it gives you the ramified part of coming from this extension. Okay, so we just plug G and H into this. And what do we find? Well, we get that, well, first I should say, what is GP mod IP? Well, that gives you the unramified extensions of QP. That's just isomorphic to the Galois group of FP bar over FP. And that's infinite, that's profinite cyclic if you want. So a group like this is something we can deal with in some ways. Okay. And from the inflation restriction sequence, we get that H1 of GP mod IP, coefficients in X fixed by the inertia group, is the kernel, let's write it on another line, kernel of the map from H1 GPX into H1 IPX. So this says, first of all, it's the kernel, and also this is a subgroup, can be regarded as a subgroup of this. So these are the cohomology classes that become trivial when you restrict to the inertia group. So we call these, and I'll have room here now, these are what's called the unramified classes. Because they're the ones that, when you restrict to the inertia group, they disappear and become trivial. And you see they're exactly the ones that come from sort of the finite field part of the Galois group, as it, of course, should happen. These will be very important next week. I mean, they're the things that this is what you use. When you see something like this come up, it's something that controls ramification is really what it's going to be used to do. Okay. But now, of course, something like this is how do you get hold of it? You write a lemma that we can actually evaluate how big this is. So let's say X is finite. Then we have the order of the unramified classes, H1, GP mod IP, coefficients X IP, is just the order of H0, GP X. See, now this is really nice, because this is an H0. H0, in any kind of reasonable situation, you can calculate what it is. I mean, it's just the things in X that are fixed by the GP. This is something that maybe has too many symbols in it, and so it's hard to calculate. So this is nice. I won't prove this. The proof is only like 2 lines, but it's probably better to move on. Let's see. Good. Okay. So now, got to get down to business on. I'm aiming it right now at Tate duality, but to do that, I need to say a couple words about cup products. So the situation is you have an x1 and you have an x2, and you take their tensor product over z, and you could call this equal to x3 if you want, but I think it's more convenient to map this to x3. And we'll call the thing that maps x3 capital phi, for lack of a better word. And now, you take a cohomology group, hi, it's all going to be the same group, g x1, and you take h upper j, and you go by the cup product to hi plus j of g x3. Okay, well, there's only two cases I really need it, and really almost just one. But let's take the easy case first. Let's take I equals 0, j equals 2. Then what do we have? Here, we just take an element of x1 that's fixed. So we call it x1. Here, we take an f that maps g cross g to x2. We got to put them together. So this goes to x1, let's call it cup f, like that. Now this has to be again in h2, so it has to be a function of g1 and g2. Well, it's not too hard to guess. It's well, there's a tensor product in here, so you take x1 tensor x1 tensor f of g1, g2. Okay, this lives in x2, this lives in x1. We can apply capital phi to it, and we end up in x3, just where we should be. If you check this, well, it's not too hard to check. This does give a cocycle, and it's a well-defined map from the cohomology groups. You can also switch the I and j and do it the other way, just as easily. Well, of course, we wouldn't be saying much about cup products if this is all there was to it. Let's do the case I and j is 1. Okay, so then we take phi1, we'll take, phi1 and phi2. Okay, this will map to phi1 cup phi2. Okay, and this has to be a two cocycle, because we're going into 1 plus 1 is 2. So phi1 cup phi2 of g1, g2 is, I have written down here. Well, I'm going to have this capital phi, just to put things into x3. Phi1 of g1 tensor g1 phi2 of g2. Anyway, essentially you take phi1 of g1, phi2 of g2, put them together with a little twist, and then send them over to x3. Anyway, the main point is it's a way to get from cohomology of level I and j into I plus j. Okay, and it happens in this case we can actually do it by an explicit formula. Okay, so let me give one example of a cut product because it relates to something we had before. Namely, let's take our A and B in QP cross and maybe take A not a square or whatever. Okay, and we can define phi in H1 of GP coefficients in Z mod 2Z. So that just has to be a homomorphism into Z mod 2. So we're just going to define phi of G equals 0 or 1. This is if G of square root of A equals square root of A, and this is G of square root of A equals minus square root of A. And we'll make psi, whatever, in H1 of GP coefficients in mu2. So this is the second roots of unity, just plus or minus 1. And we'll make psi of G equals G of square root of B over square root of B. So that's just plus or minus 1, of course. Okay. Now, we can regard mu2 is, well, one way to think of it is homomorphisms from Z mod 2Z into mu2, where this mu2 is not the same as this mu2, like that. So it's really sort of Z mod 2Z, oh boy, stars, I think what I've used in my notes. It's a dual of Z mod 2Z. Well, it is. You could also change the 2 to an n, and it would, then it becomes a little bit less trivial. Okay, so see what you have then is you have Z mod 2Z tensor mu2. Well, it's canonically isomorphic when you tensor something like that to mu2, which we make contained in QP bar cross. So we can take our phi cup psi, and this will be an element of H2 GP QP bar cross, which, if you remember, was isomorphic to Q mod Z. And if you work it through, this is essentially our F, which corresponded to the Hilbert symbol A, B sub P. I work it out a little bit more detail in the notes. Namely, you work out with the formula for the cup product I gave up there, you get a cocycle. I wrote down a cocycle here. The difference is a co-boundary. And so this really gives the same cohomology class as our Hilbert symbol. Okay, well, this can all be generalized. Okay, so let's set up a little bit of notation. We have x is finite. Order of x, let's say, is n. We can define x star is the dual. It's homomorphisms from x into the nth roots of unity. And we'll just take p as any old prime. I'll take it to be finite. There's a few technicalities for the infinite prime, which I'll ignore in the talk. If you really want to look at those, you can. It's written up in the notes what happens. Okay, x star has a g action on it. So, g is going to be GP, our Galois group of QP bar over QP. And now G can act on X star. I'm assuming G acts on X, of course. G acting on X star, acting on some element X, is just defined to be G of X star of G inverse acting on X. If you sort that all out, what that means, this gives an action of G on X star. So now we can state local Tate duality. This is a theorem proved by Tate in the early 60s, back when he was still local. So we have the groups HIGX are finite for all I, and they're actually equal 0 for I greater than or equal to 3, which is why one reason I've been ignoring H3s and above. Okay, and B, the cup product gives a non-degenerate pairing let's say for I equals 0, 1, and 2, for HI GP X cross H2 minus I GP X star. Well, now if you take X tensor X star, you get mu n. You can put that into the much bigger multiplicative group. So we make it go to H2, which of course is where the cup product is going to end up. GP coefficients in QP bar cross, which will canonically identify with Q mod Z. So we get a non-degenerate pairing like this. This is actually a very powerful thing. But then we even have more. So let's suppose P does not divide the order of X. Then we can look at the unramified classes, H1 of GP mod IP. So these are the unramified classes. Well, these are the unramified classes here. And then we have the unramified classes on the other side. And H1 GP X star, oh sorry, GP mod IP X star IP are exact annihilators of each other. In this pairing. So if you look at everything that pairs to 0 with all the unramified classes here, it's exactly this. So we can actually see that in terms of our Hilbert symbol up there. So suppose we have A corresponds to an unramified class up there. So we have our A is our phi over here, and we have our psi over here. Let's call it psi. Phi corresponds to an A, and we're going to take P not equal to 2 because of this condition. It just says if we want an unramified class, well, this is corresponding to the extension square root of A. It's easy to work through, and you see that it just means that P doesn't divide A. Or A is, well, it's a p-adic unit times a square. We throw out squares. So you can just say A is a p-adic unit. Now, if you run through all the unramified classes, A runs through all p-adic units. Now, suppose B, we'll take A, for instance, not a square, a p-adic unit that's not a square. Suppose B pairs with it and gets 1. If you look at what it means to be a norm and stuff like that, it actually forces B to be a p-adic unit. And in fact, all p-adic units are norms from an unramified extension. So you actually see that it's sort of p-adic units, and the p-adic units are the things that pair to 1 in the Hilbert symbol. That's exactly what this is saying. Because here we'd have A being a p-adic unit. We run through all A's that are p-adic units. And the thing that's orthogonal under the pairing is exactly all the B's that are p-adic units. And that corresponds to the unramified classes over here. So you can regard this as a vast generalization of something that's happening with the Hilbert symbol. Okay, let's see. I want to just say a couple more words about, let's see. Or actually, I guess this would be a good place to stop. So I'll stop.